Hey guys, welcome back to this week's video. I'm Melina, and this week we're going to be talking about aromaticity. So when we classify structures based on aromaticity, you can either have them be aromatic, anti-aromatic, or non-aromatic. So in order for a structure to be aromatic, it has to be cyclic, it has to be conjugated all the way through, meaning that all the atoms in the structure are sp2 hybridized. It has to fulfill Huckel's rule with regards to how many pi electrons it has. The equation we use for Huckel's rule is 4n plus 2, where n is just any integer. So if, for example, if you have 10 electrons, you can use the integer where n equals 2. So 4 times 2 would be 8, plus 2 would 10 electrons. So that would work. And lastly, that is planar. Secondly, if you have a structure, you can classify a structure and name it anti-aromatic. So for anti-aromatic, it's basically the same thing as aromatic, except the one difference is that instead of fulfilling Huckel's rule for the amount of pi electrons you have, it's just going to be 4n. So for aromatic, 4n plus 2, anti-aromatic is 4n pi electrons. Now, if you have a structure that doesn't fulfill it being aromatic, it doesn't fulfill it being anti-aromatic, that structure is non-aromatic. So as long as if one of the rules for aromatic structures or anti-aromatic structures is not fulfilled, that structure is going to be non-aromatic. Now let's look at the examples I've provided down below and see how they fit into each category. So this structure, is it aromatic? Is it cyclic? Yes, it is. Is it conjugated all the way through? Are they all sp2 hybridized? So let's look. sp2, 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 sp2. It's all hybridized. It's all sp2 hybridized. So the whole structure, all of these carbons have a pi bond attached to them. So yes, it is conjugated. Now, does it fulfill Huckel's rule? So let's count the amount of pi electrons involved in the structure. 2, 4, 6, 8, 10, 12, 14. So what value of n can we input into Huckel's rule to get it to equal 14? If we use n equals 3, 4 times 3 is 12, plus 2 equals 14 pi electrons, which is what we have in this structure. So it works. And lastly, it's planar. So this structure is aromatic. Now let's look at this molecule. Is it anti-aromatic? Is it cyclic? Yes, it is. It's in a ring. Is it conjugated all the way through? Are all the carbons sp2 hybridized? Remember, it doesn't just have to be carbons. It could be other heteroatoms like nitrogens, oxygens that have lone pairs, stuff like that. But for simplicity, we're just looking at carbons. And all of the carbons in this structure are sp2 hybridized. They all have a pi bond attached to them. So they all have pi electrons, p orbitals. So that works. Now let's look at the amount of pi electrons. So remember, for anti-aromatic, we're fulfilling the 4n rule. So 2, 4, 6, 8. If we input n equals 2, 4 times 2 equals 8 pi electrons. So that works. And lastly, it's planar. So this is an anti-aromatic structure. Now let's look at this. Remember, for non-aromatic molecules, that just means that one of the rules for an aromatic molecule, one of the rules for a non-aromatic molecule is not fulfilled. As if at least one of those rules is not fulfilled, it is non-aromatic. So is this cyclic? Yes, it is. It's still a ring. Is it conjugated all the way through? Is everything sp2 hybridized? So let's look. sp2, 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 sp2. What about this? This carbon right here only has sigma bonds attached. This is sp3 hybridized. So it is not conjugated all the way through. But let's just keep going through all the other characteristics just to see. Let's count the amount of pi electrons. So 2, 4, 6. We can use n equals 1, and it would fulfill Huckel's rule to get 6 pi electrons, and it's planar. But even though it fulfilled 1, 2, 3 rules out of the 4, because it does not fulfill at least one rule, that means the structure is non-aromatic. Okay, Let's see. Next, we can go on to identifying basicity. So if a structure is initially aromatic and maintains its aromaticity after being protonated, then that reaction is favorable. It's not losing its aromaticity. That means whatever portion is being protonated is more basic. It's more likely to accept a hydrogen. On the other hand, if you have a structure that's aromatic, but then when it's protonated, it loses its aromaticity, it's less favorable. So that position that's being protonated is less basic. It's not likely to accept a hydrogen. That was a lot that I just threw out there. So let's go through an example so it makes a little bit more sense. So we have the structure here. It can be protonated at this nitrogen or this nitrogen. So in the top, we have it protonating the right side. And on the bottom, we have it protonating the left side. So if we protonate, let's move this. There you go. If we protonate the right nitrogen, this structure, because it's anti-aromatic, it loses its aromaticity. So in the initial structure, there are 1, 2, 4, 6, 8, 10 pi electrons in this structure. It's conjugated all the way through, it's planar, it's cyclic. So this is an aromatic molecule. So the amount of pi electrons is 10. That's 4n plus 2, where n equals 2. But when we use, so this lone pair is participating in aromaticity. If we use this lone pair to pick up another hydrogen, the amount of pi electrons in this structure is now only 8, fulfilling 4n, which is anti-aromatic. So it's less likely, and that's not favorable just because it's going from aromatic to anti-aromatic. So because it's not favorable, it's less likely to get protonated. Now, if we look at the bottom structure where we're protonating the last nitrogen. So over here, these nitrogens are not participating in aromaticity. They're not part of the pi electrons. So if we use those lone pairs, if we use this lone pair to pick up another hydrogen, get protonated, the structure still maintains its aromaticity. It's still cyclic, it's still conjugated all the way through, it's planar. There's still 10 pi electrons, 2, 4, 6, 8, 10. So it's still going, after being protonated on the left side, it's aromatic here, and it's still aromatic here. So because protonation of the left nitrogen does not affect aromaticity, it's more likely to get protonated, meaning that the left nitrogen is more basic. This is more likely to act as a base and pick up another hydrogen. And yeah, thanks for watching, guys.